Hello, class. We're doing the second part of 11.2. It's going to be a fairly short lesson, so it shouldn't take us that long. I'd like to recall this problem we did in the last section. You recall we're looking at hypothesis tests, testing the mean of 3 or more samples. We did this problem, so I'm hoping that it looks familiar to you. We looked at each physician. They all met a certain amount of patients, and they took about this many minutes. We ran the test, if you recall. The test looks something like this. The null is always however many populations we have. We set them equal to each other, assuming that they start off equal. If we have evidence, we can conclude that there's at least 2 means that differ. This particular one, we did a rejection region or a critical value. The F statistic was in the rejection region, so we had sufficient evidence to reject the null and conclude, here's what I really want us to focus on now a moment, conclude that there are at least 2 physicians that have different mean times. That means at least 2 of these do not equal each other. At least, there might be more. That was a significant F test. It tells us that, again, treatment means of the group are statistically different. But the next logical question is, and it hopefully is one that you might have already been tempted to ask, and that would be, well, which ones are different? Which ones are different? ANOVA does not tell you which or how many pairs of means differ statistically from each other. Only that at least 2 of them do differ from each other. If I have K treatment means, in other words, we had 4 physicians, K was 4, there are C different means. This is a combination of possible comparisons of 2 means. C here is equal to basically a combination of K take 2. What do I mean by that? Well, there are 4 groups, and we're taking them 2 at a time because we're comparing 2 means against each other. We can run that through on our calculator if we want, but that'll turn out to be 6. What are the actual differences? It's the difference between 1 and 2, the difference between 1 and 3, between 1 and 4, between 2 and 3, 2 and 4, and 3 and 4. All of those differences are differences that we have to consider that might be statistically different. The number of these, 1, 2, 3, 4, 5, 6, is our K take 2. It's always 2 at a time because I'm comparing 2 of them every time. But K is the number of groups or populations that we're dealing with. What we're going to be doing is looking at confidence intervals to be able to answer that question, which ones do differ. There are really 3 types that are pretty common out there. These are the 3 types. The most common is the Tukey method, and we'll look at multiple types here today. In each technique, the confidence intervals are constructed around the differences. Remember, when I'm looking at 2 of them, I'm looking at the difference between the means. The difference, keep that in mind. The selection of the technique is based on the experimental design, in other words, which one I'm going to be using. Most of the packages, computer printouts, will give you some help in determining these. We are not going to be asked to produce these. I'm not going to expect that you can, but I do want you to be able to read their results off the computer and understand what they mean. That's our focus here today, is looking at these differences. We want to be able to understand what that means. The data that we had this takes us back here a moment. Back to these, if you recall, the 4 physicians. The mean of number 2 was the greatest one. The mean for number 4 was second greatest. Mean for number 1 was third, and the mean for number 3 was the smallest. Hopefully, it's obvious to you that if the test showed that there was a difference that was statistically significant, we would know that the greatest one and the least one are for sure 2 of them. The greatest one compared to the smallest one has to show a difference if the test proved that there was a difference. But the real question now is not just these 2. We know those 2 are statistically different. But the question is what about the first 2? Are they statistically different? What about the first and the third? What about, we said the first and the fourth would be, what about second and third? These 2 right here. What about second and fourth? And what about third and fourth? Those are what we're considering at this point in time. Here are some 95 confidence intervals. Notice again, we're looking at differences, minus, 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 all the way down. Notice this confidence interval is entirely negative. We're 95% sure that the mean of population 2 is greater than the mean of population 1. And the reason we're sure of that is that the differences were entirely negative. That means that I needed a smaller number minus a larger number. I am now statistically sure that there's a difference, 95% sure that there's a difference between these 2. But look at 1 to 3. 1 to 3 goes from a negative to a positive. That's crucial there. Look at the signs here, negative to a positive. Well, if it's a negative difference, that would mean 3 was bigger than 1. But if it's a positive difference, it would mean the first one's bigger than the second. Or it could be 0, which means they're equal. Because of that, if I were to run a hypothesis test between these 2, it would likely show up as insufficient evidence. We would have to continue to assume that they're equal. This one is entirely negative. So I am 95% sure that 4, the mean from population 4, is bigger than the mean from population 1. This one's entirely positive. That means I'm 95% sure that the mean from population 2 is bigger than the mean from population 3. This one goes negative to positive, means I'm not sure, could be 0, could be negative, could be positive. Either one could be larger, or they could be equal to each other. This one's entirely negative, so I know that 4 is larger than 3. I've put these same intervals on this next slide. They're right up here. I put the means that we had from each population group on here as well. See if this makes sense now. This one was entirely negative, which means we're sure, 95% sure, the mean from population 2 is bigger than 1. Well, here's 2, here's 1. That would make sense. 2 was bigger than the 1. This one went from a negative to a positive, means we're not sure. 1 and 3, right here they are, the bottom 2, they're pretty close. We don't have evidence that they are different. 1 and 4 is entirely negative. 4 must be larger. Here's 4, here's 1. The difference between them is big enough to indicate that we have a difference that would be statistically significant. 2 and 4 go from negative to positive, means they could have a difference of 0. That means we're not sure between 2 and 4. Well, here's 2 and 4 up there. They're close enough where we don't have evidence that there's a difference. 3 and 4, entirely negative, which means 4 must be bigger. 3 and 4 are these two. The 32 is far enough away from the 27 that we have evidence that they're different. How would I say that? Well, let's take a look at the first one, 1 minus 2. I would say the mean time spent with patients by physician 2 is larger compared to number 1 and 3, but not statistically larger than 4. It was larger than 1 and 3. That was number 2. It's larger than 1 and 3, but 2 and 4 were too close to call. The next one, the mean time spent between patients by physician 4 is greater than 1 and 3. 4 was greater than 1 and 3, but not statistically different than 2. 4 was not different than 2. That's how we would answer those questions. Next, we're going to look at just some computer printouts, and I just want you to be able to read and understand what these mean. Here I had physician 2, 4, 1, and 3. You recall that was the order of their sizes. 2 was largest, 4, 1, and 3. 2, 4, 1, and 3. We're going from largest to smallest. Notice that these two are in the same column. That's this printout's way of saying they are not statistically different. Notice these two are in a different column. That's saying those two are not statistically different, but these two are different from these two. We're saying 34 is statistically larger than 28, and it's larger than 27, but it's not larger than the 32. We're saying 32 is not different or less than 34, but it is greater than these two. This 28, we're saying it's not statistically different than the 27, but it is statistically different than those two. The 27 is not statistically different than that one, but it is statistically different than the first two. A lot of statistics in there. Here's another printout. It's got these two marks. Because these two are connected with the mark, it means they're not statistically different. But 2 is not connected. There's a break here with 1 and 3. So 2 is larger than 1 and 3. 4 is not connected, so 4 is larger than 1 and 3. 1 and 3 are connected, which means they're not considered different, but there's no connection with these back up to the first one. Let's see if we pick that up. Notice these overlap, okay? They overlap. Let's make sure we understand what this one means. I made these up, okay? But notice 2 is not connected to any of them this time. That means 2 would be larger than 4, 2 is larger than 1, 2 is larger than 3. There's no line connecting 2. It's statistically different, statistically larger than all the other ones. Number 4 is connected to 1. So 4 would statistically be less than 2, it's not connected. 4 would be not statistically different from 1 because they're connected. 4 is not connected to 3, so 4 is statistically larger than 3. 1 is not connected to 2, so 1 would be statistically less than 2. 1 is connected to 4, so 1 is not statistically different from 4. 1 is also not statistically different from 3. So 1 really is not statistically different from any of them except 2. 3 is not connected to 2, so 3 is less than 2. 3 is not connected to 4, so 3 is less than 4. 3 is connected to 1, so it's not different from that. Try stating how all of these compare to each other. You have 6 comparisons, 2 to 4, 2 to 1, 2 to 3, 4 to 1, 4 to 3, 1 to 3. Think about what you would say for each one. Your answer would have been 2 is not different from 4. 2 is larger than 1. 2 is larger than 3. 4 is not different from 2. 4 is not different from 1. 4 is not different from 3. 4 is not different from any of them. It's connected to all of them. 1 is less than 2, but 1 is not different from 3 and 4. 3 is less than 2, but 3 is not different from 1 or 4. Again, try stating this one. I'll give you a little bit of time to do that. Here we would say 2 is not different from 4, but 2 is larger than 1, 2 is larger than 3. 4 is not different from 2, 4 is not different from 1, 4 is larger than 3. 1 is less than 2, but 1 is not different from 4, 1 is not different from 3. 3 is less than 2, 3 is less than 4, but it's not different from 1. I made up new intervals. I would like you to look at these comparisons once and check all of the comparisons. I'm going to write them out here once. Actually, I guess you can do it right from here. Here are all 6. Think to yourself, are they statistically different each time? And if so, which one is larger? Go ahead and take a few minutes and try those. Your answers, because this goes from a negative to a positive, 1 is not different from 2. Negative to a positive, 1 is not different than 3. Negative to a positive, 1 is not different from 4. Positive to a positive, we know that 2, we're 95% sure that 2 is bigger than 3. Negative to a positive, we're not sure that they're different. We got to assume they're equal. Negative to a negative means we're 95% sure that 4 is bigger than 3. As I promised, this was a short lesson today. Good way to have a Friday. There's no new assignment. We had a section 11-2 assigned this past Wednesday. It's due next Monday. Basically, it's the problems right off your syllabus. Hopefully not too challenging. We'll see you then on Monday.